Welcome to Ask and Learn.
In this problem, which is a lot simpler than the last problem, we have a wheel here. A wheel here that's attached to a spring that's then attached to ground, and this thing is rolling without slipping. And it looks like this spring is attached at the top point of the wheel here. So there's two different cases that actually could be happening. Whether the spring is attached to the top point of or point on the wheel circumference, which means that, like, if it rolled way over here, you'd have the spring, end of the spring here. Or it could be the case that there's something wrapped around here, so that the end of the spring is always at the top of the wheel here. Because we're talking about small angles here, the distinction between those two cases doesn't matter. So we can just look at the easier case when we're assuming that this spring is always attached to the highest point on the wheel. Again, it wouldn't really matter, because we could figure out the change of length of the spring just by knowing where this point was after this thing rolled. But that would be a very messy expression. And then if we simplified it for small angles, we just get the same as we would here, as what I did here. So we know that this point moves. Okay, so the spring length changes, and that the distance at this point moves is 2r times theta. Okay, so again, this point moves r theta, and then this point moves 2r theta as theta rolls. So the change in length is 2r theta, so we have 1/2 k times 2r theta squared. Now the kinetic energy, there's no gravitational potential because the center of mass of this wheel doesn't move vertically. So the kinetic energy is the kinetic energy about the center of mass plus the rotational energy about the center of mass plus the translational energy of the center of mass. This we were given in JCM, we were given in terms of a radius of gyration, so that is m times kcm squared. The velocity of the center here is r theta dot, so we have 1/2 m r theta dot all squared. And so that reduces to this expression here. So what we can do is we can look at for our equivalent stiffness, and we can see that that's just this term here. So that's 4kr squared. And then our equivalent mass is this term here. And once we know those, we can figure out what our natural frequency is. So that's 4kr squared all over m kcm squared plus r squared. We have values for all of those things. So plugging them in, we get the natural frequency is 8.12 radians per second, which means the natural period is 0.774 seconds.